Welcome back to the classroom. Today we're going to be doing another of these explain exam question papers. This one will be the additional physics sample paper. This is on module 7 and we're going to go through all of the relevant multiple choice questions that's on this paper. So the very first question, it says James Clerk Maxwell made significant contributions to physics. Which of the following did Maxwell not contribute to our understanding of physics? Is it A, predicting the velocity of electromagnetic waves, B, predicting the existence of electromagnetic waves, C, validating the existence of electromagnetic waves, or D, unifying electricity and magnetism through equations? So the answer for this is actually C. He didn't actually validate the existence of other electromagnetic waves. He did predict the existence of a electromagnetic wave spectrum. Just a bonus here. The person who actually validated the existence was a guy named Heinrich Hertz, and his discovery was on radio waves. Okay, so there we have that. Let's move on to question 2. So on to question 2. I'll just scroll down a little bit here. So we have a red giant star in our galaxy, and we have the following facts about this star. Fact number 1, its distance from us is 640 light years. Fact number 2, it has a surface temperature of 3,500 Kelvin. Fact number 3, its atmosphere contains titanium dioxide. Fact number 4, it is moving away from us at a speed of 21.9 kilometers per second. Which of the given facts about this star cannot be determined from its spectrum? Okay, so in a question like this, where we're trying to work out spectra, we need to firstly remember spectra can tell us things like chemical composition. When it comes to chemical composition, spectra are formed because the ray of the sun, so if we have the ray of the sun, if we have an absorption spectra, it's because of the different types of gases that's in the atmosphere absorbs a specific wavelength of light. And so we see the absorbed wavelength when we detect it on our spectras. So definitely we can work out the composition is titanium dioxide. We can also work out the surface temperature. If you recall, the intensity of the lines or the quantity of the different colors of light can also tell us the surface temperature. And as we said before, with the Doppler effect, you can certainly work out how fast the object is moving towards you or away from you. So the only other option remaining is distance. We can't actually tell the distance of a star using spectra. We actually need to work out through a different way. So let's go through question 3. Okay, question 3, it says, which statement describes how an electromagnetic wave is propagated? So electromagnetic wave, we have an oscillating electric field, and when we have a constantly changing electric field, we would expect a constantly changing magnetic field that's oscillating perpendicular to our changing electric field. Okay, so constant, so it definitely can't be A because it says constant. An oscillating magnetic field causes an oscillating electric field parallel. We can't be parallel. So we're looking at the keywords of perpendicular. So an oscillating electric field causes an oscillating magnetic field to the electric field. Magnetic field causes constant. So C is our answer, because to get an electromagnetic wave, we are trying to see constant changes in both the electric field and the magnetic field. There shouldn't be a constant value in there. Okay, so let's move to question 4. Okay, This one is a bit more of an analysis question, so I'll just zoom out a little bit. We have Anna and Bo carried out an independent experiment to investigate Malice's law. They graph the results of their experiments and they see the following. Okay, based on two graphs, which of the following is correct? Now, without looking at the choices that we have, let's just firstly look at the graph itself. Okay, if you actually look at it, the shapes look relatively similar, which is great. Malice's law, if you recall, the actual formula for writing it is I max equals IO cos square theta. Okay, so we should see sort of a cosine graph like that. So we are seeing that pattern there, which is great. However, Bo's graph is actually much better. The reason being is if you look at this, the range of the data, forget whether it starts at 0 or not, it doesn't really affect what we're looking at. But the fact that it goes from 0 to 1.2, while this is 0.9 to 1.005, the range of this, the range is small. To know if we have a good database, if we have a good reliable trend, we need a very large range of sample. You can see here with the angle as well. This is a very large angle range. We want that. Okay, that's what we're aiming for. Let's go through. Okay, question A, or point A. Anna has taken more measurements than Bo, but used a better range. Obviously, that can't be true. Oh, wait, let me reread that. Misread it there. So Anna has taken more data points than Bo, but Bo has a better data range. That is true. That is true. But let's read the other ones just in case, if there is a better one. Bo's graph is more precise as angles in Anna's graph are too small. So again, talks about the precision of the angles. Anna's graph is more valid than Bo's. That one is definitely incorrect. So we can definitely take that out. Anna's measurements are more reliable. Again, that is not correct either. So let's have a look at how many points. So according to this graph, Anna has taken more data points from the looks of things. 7 data points, whereas Bo has taken only 5. But 5 is a sufficient amount of data points to give you a trend line. So that's okay. So let's see, more precise angles, too small. We would say A. Anna has taken more measurements, but Bo has used a better data range. In terms of precision, precision is how close we are to the exact answer. You can't really tell that from a graph. You have to look at other things. So precision is not something you can tell using a graph of data. Okay, module 7, question 5. A monochromatic light, meaning by a light source of a particular wavelength, let's just say lambda, strikes a double slit and produces a bright and dark fringe on the screen. So if we assume these are the bright patches, and then everything else here is a dark patch, like so. I did try and convert this from PDF, so the some images are gone, so unfortunate. Okay, so what's the difference in length between P1 and P2 in terms of the pathways? Okay, so according to the formula, we have lambda d sine theta, lambda, that's our relationship there, and lambda. So n means the order we see the wavelength in. We are looking at a bright band. Let's see, are we producing a bright band or dark band? So light from slit 1, pathway 1, slit 2 to produce the dark fringe shown. Okay, so just had to look at the original image again. So this is our center bright band. So this is N0, our center bright, or our N1, sorry. So that's our bright band, which means this is 0.5, or N is 1.5 of the dark band that we have. So we're in the first, and then we're at the second bright band. Okay. Just readjust. Center bright band. So if we're in the second dark band, we're looking at a wavelength of 3/2 wavelengths. Okay, because if the center band is 0, or center bright band, and the first bright band next to that is a whole number integer, then this one is n equals to 1.5. So here, 1.5 lambda, which is the same thing as 3 lambda over 2. Okay, so that's how you do that question there. All right, question 6. This one is about intensity. Okay, what is the best estimate of the temperature of this black body? So here we have, you need to draw out, this is using Wend's law. And Wend's law states that the temperature, the maximum intensity wavelength is given by the Wend's constant divided by temperature. So wavelength max, okay, oh wait, we'll swap it around. So temperature is equal to B over lambda max. So our wavelength that we have here is, let's say, it's close to 500, but I don't think it's quite. I feel like it's a little bit behind. Let's call it 480 nanometers, so we'll convert that into meters. Then we substitute in the value for Wend's constant, which is about 2.898 10 to the power minus 3. So if you plug that into your calculator, you should be able to find a nice numerical answer. So plug that in. So I get roughly 6,037.5 Kelvin. So let's find if we have something of that range. Okay, so that would be A there. So the closest one to it, obviously I could have simply misread where the dots are because I'm not using rule. It could have been 500. So the answer to that is A, and supported by this one here. Okay, we move to question 7. The graph says the maximum kinetic energy of the photoelectrons emitted are shown for X and Y. It also says that the metals are illuminated with a light with a wavelength of 450 nanometers. Now, just for our sake, because it says what would the effect of doubling intensity be? Now, intensity is related to the number of photons. So we're going to increase the number of photons. But let's firstly see, will it affect X and Y, or will it affect only one? Okay, so we know that from the wave formula, velocity, in this case speed of light, equals to frequency times wavelength. So the frequency of the light source is going to be our speed of light times this wavelength that we use. So the answer I got was 6.67, or approximately at that form, 10 to the power 14. So it means that the light source range is around here. So we will get a photo emission for X, but we will not get an emission for Y. So if I read through the questions here, I can simply forego the explanations if they include X and Y, because that's not part of the response. If I look at A, it says the number of photoelectrons emitted would not change, but the maximum kinetic energy would increase. That's not the case. Intensity doesn't change the energy. So it says the number of photoelectrons would increase, but the kinetic energy remains the same. So for number 7, it's B. This one is band 5 to band 6 response. So good on those who managed to get this one right. Question 8, we have a spacecraft sitting on its launch pad, measured at length L. This spaceship passes an outer planet at the speed of 0.95. Which observations of the length of the spaceship is correct? So this goes back to frame of reference, and this is sort of one of the things that gets a bit trippy for people. So let's just draw our not so round planet, and then we'll draw our rocket. Everything has to do with frame of reference. So how does one thing see itself to another? Okay. Now for the pilot, if you are sitting in the, if you're the pilot sitting in the spaceship, to reference it, you are traveling technically at 0.95% of the speed of light. But if you are the observer, so this is your reference, you would observe, I'll just get rid of that. You would observe, if we're looking at your frame of reference, so we'll do it in a different color, your frame of reference, you'd see the planet moving away from you at 0.95% of the speed of light. Okay? If you were a person on the planet, and so we changed our colors back again, you would look at the person moving at 95% of the speed of light. Okay? So that's kind of the frames that we need to put in. So the observer on the spaceship, okay, what observations of the length of the spaceships are correct? So if you're on the spaceship, you wouldn't see a change because that's your own frame of reference. You don't see anything occurring. To you, it looks the same. Same idea with, and the most important part is, I guess, how Einstein defined special relativity, right? The whole concept of special relativity is you can't violate two postulates. Postulate 1 says that if you travel at the speed of light, you wouldn't be able to tell, or principle of relativity holds true. So if I'm traveling at a constant speed in the spaceship, I shouldn't be able to tell if anything's happening. Okay, so that's kind of also why I shouldn't see a change. If I'm an observer on the planet, so this person here, do I see a shorter length or a greater length? Well, shorter length, because it's length contraction for a reason, right? So A is the correct answer for question 8. As you can see here, that's only 2 to 3 as a band. That explanation sounded a bit more tough, higher than 2 to 3, but it is what it is. Okay, question 9. What is the magnitude of the momentum of an electron traveling at 0.8% of the speed of light? So this is requiring you to use the momentum formula. So we know that momentum is mass times velocity. And then we have this value here. So we can plug 0.8 C into this formula here, 0.8 C into this formula here. And then we can write the mass of the electron, which is 11 times 10 to the power of minus 31. If you plug that into your calculator, you will get B as your answer there. Okay, so that's how you do that question. Just make sure when you substitute C, you could, in this section here, once you've substituted, you could rewrite it so it'll look like this. Okay, it'll look like that. So you could simply rewrite it as 0.8 because the two C's would cancel each other out. Okay, but don't forget the 1 at the bottom, or else your square root wouldn't work. Okay, and our last one is question 10. So this one, it says we have 4 cesium clocks flown twice around the world on commercial jet flights. If you recall, this was one of the ways we demonstrate that special relativity does exist. One eastward, one westward. The traveling clocks were compared with reference clocks at the US Naval Observatory, and the results were compared with predictions from Einstein's theory of special relativity. Which of the following is correct about the observed results in relation to Einstein's theory? Both supported the idea that special relativity exists because you can see the times are different. Okay, the times are different. It doesn't really matter if the predicted time is a bit different from the observed time, that being because the predicted time is still not at the same time frame as what's recorded on Earth. So given that we have these changes of time, that kind of explains and proves special relativity and relativistic effects work. All right, thank you for joining me up to this point. If you found videos like these explaining exam questions useful, please give it a like and subscribe. I'll see you next time. We'll go through some other questions in the future as well.